In part 4, we're going to consider area and volume involving e to the x. So in this first problem, we'd like to find the area that's bounded by the curves y equals e to the negative x, y equals 0, x equals 0, and the vertical line x equals 1. So we're looking at this sort of trapezoidal shape. I'll outline it in red. And this is the area that we'd like to find. Well, area under a curve involves an integral, and our integral is going from 0 to 1. So we're looking at the integral from 0 to 1 of e to the negative x dx. When we integrate this, we end up with negative e to the negative x from 0 to 1. And if we substitute in 1, this ends up being negative e to the negative 1 minus, let's substitute in 0, negative e to the 0. Now I'm going to simplify this a tad. This will be negative 1 over e plus 1. Or if you prefer, 1 minus 1 over e would be the area of that curve. Let me set up another problem involving some different functions. Here we're considering the function y equals e to the x over 2 plus e to the x. So it's a function that's increasing very, very slowly. Notice that when x is 0, we would have 1/3. So we know it's crossing the x-axis at 1/3, and it's just increasing very, very slowly. And we're just considering this region in here. So again, kind of an odd function. I could plot some points if I didn't have a calculator to help me get a picture. But I'm just trying to find the area of that shape. And so we're looking at the integral from 0 to 1. I'll take that back. It's not going to be from 0 to 1. We're bound by y equals 0, which is the axis, and x equals 1. So this portion of our curve isn't boxed in yet. We're going to need to figure out when this curve equals 0. Will it ever equal 0? Alright, well, given that we wouldn't know how to deal with that situation yet, we're going to add a parameter to this problem that I believe should have been there, that this also should have been bounded by x equals 0. And so we'll return to what we were thinking originally, that the area we're trying to find is that piece right there. So we'll be integrating from 0 to 1 the function e to the x over 2 plus e to the x dx. Notice that in this case, if u equals 2 plus e to the x, then du equals e to the x dx. So we can use some U-Substitution here. This will be the integral of 1 over u du. Our limits of integration will become, when the upper limit, when x is 1, 2 plus e, and when x is 0, it'll be 2 plus 1, or 3. When we integrate this, we end up with the natural log of the absolute value of u from 3 to 2 plus e, and by substitution then, this will be the natural log of the absolute value of 2 plus e, which is positive, minus the natural log of 3. Let's consider one more. We're going to find the area that's bounded by e to the x sine e to the x equals 0, and y equals 0. Make sure you're in radian mode when you graph this, and you'll see that this is a pretty cool looking graph. X equals 0 being the y-axis, y equals 0 being the horizontal axis. So our graph looks something like this, and this is the only portion, this part right here, that we're concerned with, but this graph gets kind of cool as it just oscillates back and forth, getting wider and wider and wider. That would make sense as e to the x is growing. But we're concerned with finding the area here. So we need to know what's the first place that e to the x returns, that our function returns to the axis. And so some things to think about. We're trying to locate this point right here. Our function is e to the x times sine of e to the x, and we know that e to the x will always be positive. So we need to think about the sine value. When will sine of something equal 0? Well, the first time sine equals 0 is at sine of 0. And then the second time that sine equals 0 is at pi. So we'll reach our point of intersection when e to the x equals pi. And this is strange to solve for, but we could solve it by hand by just converting back to log form. This is the same thing as the natural log of pi equals x. That's the x value, which tells us about our integral. Our integral is going to go from 0 to the natural log of pi, and we're integrating e to the x times the sine of e to the x dx. Now, this might be tricky to follow, so let's use U-substitution. If u equals e to the x, then that means that du equals e to the x dx. So we would be integrating the sine of u du, and our limits of integration will change. Our lower limit, when x is 0, becomes e to the 0 power, or just 1. Our upper limit becomes e to the natural log of pi, which is just pi. When we integrate sine, we end up with negative cosine of u from 1 to pi. Substituting in pi, we would have negative cosine of pi minus negative cosine of 1, which I don't know offhand, but I do know the cosine of pi. The cosine of pi is negative 1, so this will be 1 plus whatever the cosine of 1 is. That will be our area. In our next problem, we're finding a volume in the first quadrant for the region that is bounded by y equals e to the x over 2 and x equals 2. So this space is being rotated about the x-axis. So we're going to have a bowl-looking shape that might look something like this. We're done. We've got horizontally oriented circles, which means everything will be in terms of x. We'll be integrating from 0 to 2. And since they're circles, we have to recall that this is pi times our radius squared, and our radius in this case is e to the x squared dx. Now recall, by power to a power, if we clean up this integral, this is pi times the integral from 0 to 2 of just e to the x dx. The integral of e to the x is itself, so we've got to evaluate e to the x from 0 to 2 and then multiply the result by pi. This will be pi times e squared minus e to the 0, which is 1. And so this would be an expression of our volume, pi times e squared minus 1. Finally, sometimes we'll be dealing with exponential functions that have bases other than e. So the base can be anything besides e, and so we're dealing with a function of the form y equals a to the x. And one of the things about we need to memorize at some point, you'll just want to have memorized how to take the derivative of such things. Now let's show where it comes from. A to the x power is equal to e to the power of the natural log of a times x. Right? These are equivalent expressions. And so we know that the derivative, if y equals this, e to the natural log of a times x, then to take the derivative of this, we know it's going to be itself, e to the natural log of a times x, times by the chain rule. Recall that the natural log of a is just a constant, so this will be times the natural log of a. And if we convert this back to our original statement, e to the natural log of a times x was equivalent to just a to the x, so we're going to end up with a to the x times the natural log of a. Another way to say the same thing or deal with the same rule is the derivative of an exponential, a to the x, is always itself times the natural log of the base. And this was true, this is exactly true if the base was e to the x, but the only difference is you end up with itself times the natural log of e, and the natural log of e is just 1. So that again confirms that it must be e to the x. And sometimes we'll have to deal with the chain rule. Let's do 3 examples. Let's find the derivative of y equals 5 to the x. Well, by our rule, this is just itself times the natural log of the base, in this case 5. Second example, if y equals 3 to the x squared minus 2x power. Well, the derivative is itself, so 3 to the x squared minus 2x, times the natural log of the base, which is 3, and now we've got to invoke the chain rule, which is the derivative of the exponent, which would be 2x minus 2. Right? Can't forget the chain rule. Final example of this, if y equals x times 6 to the negative x. Well, we can use the product rule here, and we'll have 1 times 6 to the negative x power plus x times the derivative of 6 to the negative x is itself times the natural log of the base times the derivative of the exponent, which in this case is negative 1. And I'm going to keep the habit of factoring, just doing it automatically so that when it's necessary I don't even have to think about it. This is 6 to the negative x times 1 plus, this will be actually minus the natural log of 6 times x. So there we have the derivative of exponentials with different bases.